Hello, and welcome back. Playing a little bit of catch up. This is day 5, 2022. Let's get into it. All right, so basically for this problem, we get some weirdly formatted input. Essentially, we have some number of stacks of crates, and then we have a list of instructions that tell us to move some number of crates from one stack to another. And important to know is that for part 1 at least, when it says to move like a stack of 3 or a stack of 2, the crane moves the boxes one at a time. So when you're moving a stack, it's going to be, it will appear on its destination stack in reverse order because the crane will move the top one first, it becomes the bottom of the new stack, etc. So you do a bunch of move operations, and then the question is, what crates are at the top of each stack when you're done. So, all right, fair enough. As usual, you know how this goes. We will get our input 5.txt1, and actually, you know what? For this problem, I'm going to be using the test input, and because it'll make it a little bit easier to explain things without stuff running off of the screen, and then at the end we'll just run it on the normal problem input. Okay, so our input is split into two halves based on this empty line. This is a lot like day 1. I've started picking up this trick where I can do signum length for each partition right tech. And this signum basically multiplication symbol by itself in the monadic form. Positive numbers become 1, 0 stays 0, and negative 1 becomes, or negative numbers become negative 1. So it serves as an input to the left side of the partition function without me having to swap it around. That splits it into two halves, and we will assign these to S and I guess, for stacks and instructions. Let's process the stacks first. So if we mix S, you can see that the problem is that our stacks are vertical, which makes it a little bit harder to parse. Let's just assign this to S, and then if we transpose it, or no, sorry, first let's filter the columns. So if we take the last row of S, we get 1, 2, and 3. And what we can do is we can just say where space does not equal that last row. This gives us a Boolean vector, which we can use to filter the columns of S. So now we're down to just letters. We can do a neg1 drop to take off the last row. Now we're left with our letters. And if we transpose them, then they become horizontal. So this is going to be a lot easier to parse. We can break it apart. And the problem is that we still have these spaces in here, so we want to take those out. And we can do for each without jot space. So we're just removing the spaces from each cell here. That gives us this, and if we mix this together, then we get a matrix, and I'll just enclose this so you can see where the boundaries are. So I'd like to represent our stacks as a single matrix. It's probably easier in this problem to use like nested vectors, but I like matrices, should be the motto of this channel. And I have kind of a cool solution that only works if it's in matrix format. Now the problem with representing our stacks as a matrix is that it's conceivable during the move operations that all of the boxes could end up in a single column. So we need to make sure that our matrix is wide enough, has enough space to support that. So before we mix like this, I'm going to assign this to S. So S is this nested list of vectors. We can enlist it to get all the letters. And then if we take the length, I would like to, hang on. So enlist length. I would like to take for each take. And what this will do is, wait a minute. What's my S here? Oh, because I, okay, give me a second. Let's start over. So we have this. Actually, I'm just going to start editing file so that we don't lose all of this. This is going to make it kind of easier to follow along, I think. So we have stacks and indices parsed from our input, and then we are building this thing, so we assign that to S. S is a nested list of matrices. All right. And then what I want is in list length S take for each S, and this will extend it so that it supports a bunch of spaces. And then if we mix it, then we get our matrix. And if I close this, then you can see just based on the border, doesn't have to be enclosed, but it's just for visual purposes, that we have spaces enough to be able to handle it if all of the boxes are in a single column. So this can go here, and this can go here, and this is our final sort of process stack. So if I run these and then I run S, we get our nice matrix. Again, enclose lets you see that we have enough spaces for this. All right. And then we have our instructions, which is pretty easy to parse. We're basically just interested in the numbers. So that's quad D, jot, membership, commute, partition, right for each, like so. Let's also execute all these so we actually get numbers. And then I'm going to enclose S and put it in the front here. So now we have a vector like this, and if I reverse it and then assign this to I, now we have a reverse list of instructions with our stack on the end. Now, why did I do this? Eventually, we're going to be able to use APL's reduce operator to basically consume the directions right to left, and then we'll end up with our finished matrix at the end of it. Remember that reduce works right to left because it's literally like putting a function between each of the terms in a vector, and APL is evaluated right to left. So that's why you have to do this reverse thing and make sure that our starting value is on the end of the list here, and then the instructions that we want to consume are in reverse order. So that's our list of instructions. Now, I have an interesting way to solve this problem. Basically, because it's represented as a matrix, we have the opportunity to solve this problem entirely by doing matrix rotations, almost like solving a Rubik's Cube. And I can show you how that works. So if we do a neg2 take of I, we get the last two elements, and we can reduce a function between them. Our instructions are going to be the left, or they'll be alpha, and we have three items. We have the amount that we're going to move from one stack to the other. We have an index for the stack that we're moving from, so I'll call it F for from. And we have an index for the stack that we're moving to, so I'll call it T for to. And then we can say, okay, at the from stack, we want to rotate by the amount of boxes that we're taking. So what we're doing here, this instruction says move 1 from 2 to 1. And rotate, the way that it works is positive numbers rotate to the left and negative numbers rotate to the right. So what we're saying is at the at the index of the from stack, which in this case is the second row, um, rotates left whatever amount of boxes that we want to take. And the way that we parsed our input, the tops of the stacks are in this leftmost column. So it's easy to just rotate the boxes that we want to take off of there. And so, okay, now what? Well, we can transpose this. That gives us this. And then if we flip it vertically, now the boxes that we've rotated off are sort of hanging out here in the top rows in empty space, and we can manipulate them. So what we want to do is we want to rotate them over to the column where we want to place the boxes, right? And so we can say, we can say at iota amount. This basically, what we're saying is, we've rotated some number of boxes to the topmost rows here, and iota amount will allow us to operate on all of the rows that we've just rotated into. And we can say rotate by from -2. Okay, so rotate, positive numbers go to the left and negative numbers go to the right. So if we were moving boxes from 5 to 3, let's say, then 5 minus 3 is 2, which is correct. We want to rotate our boxes, 2 columns to the left. If we were moving from 5 to 7, 5 minus 7 is -2, which means that we're going to rotate right by 2 columns, which is correct if we wanted to move from 5 to 7. So if we do this, now all the boxes that we've rotated off are now, they're rotated horizontally into the destination column. Now we have to do one more thing here, which is that remember in part 1, for part 1, the boxes, when we move them off of a stack, they get placed onto their destination stack in reverse order because the crane is moving them one at a time. So what we need to do is we need to say, what is this? Is it a top? Yes. So we want to say, and we want to rotate the set. So a top says, in the first X number of rows, X being the number of boxes that we're moving, first we rotate them horizontally to their destination column, and then we can reverse the list of boxes that we're moving within the same range of indices. Okay, it doesn't really matter here because we're just moving one box, but you can imagine that's what it's doing. Okay, and then we just have to put it back into its original configuration. So that's going to be a vertical flip and another transpose. And now we're back here, and all we have to do is rotate our boxes into the correct stack. And that's going to be at the 2 column, so at T, we want to rotate by -A, right? Because we're rotating to the right, we're moving A being amount, so we're moving a number of boxes, and we want to rotate it right, like so. And this is one complete move. So I think this is kind of cool because it's kind of like solving a Rubik's Cube or something. You sort of shift off the boxes that you want to rotate. You then rotate those, vertically. You reverse the order of them, and then you shift them into their proper place. And you can only do all this if you represent your stacks as a matrix. So I think it's kind of neat. Okay, so this DNZCMP, remember that our leftmost column in this configuration denotes the top of the various stacks. So DNZCMP, and if we look at the test output after one step, that does indeed look correct. What we can do is we can run it on the entire input by doing a reduce on I. So remember that I has our it has our stack in the last position, and then it has a list of instructions. So we could just reduce on I, and we get a final configuration. Now, in order to get the in order to get the boxes that are on top of all the stacks, we can just disclose this, and then we take the leftmost column, like so. CMZ should be what's on top. And indeed, for the test input, it looks like that is correct. So let's do this. Let's say that f, this is our function, and we'll put this on our file that we're building up here. Oh, I haven't added the line for processing our instructions, so I'll do that. This is I. And then for part 1, we are basically saying f reduce I disclose leftmost column. So if I run all of this, I should get CMZ. And indeed I do. So if we change this to run it on the test input, which is going to be 5.txt, we get this value, ZWHVF something something, which is indeed the correct answer for part 1. Okay, now part 2, the only change is that the crane can now move multiple crates at once. So we don't have to do this reversing when we're moving crates from one stack to another. Now we could just like replicate, the functionality in F, but much like my last video where I used, was it day 4 or day 3? I forget. It's all kind of a blur. But I used an operator this year, and so we can do this again here. We can basically say f is an operator, and it takes an additional function here to determine whether or not to reverse the boxes that we're moving from one stack to another. And if we do this, and I'll replace my implementation of f, then our part 1 answer, all we have to do here is we just have to add this reverse first. And then for part 2, we don't want to do any reversing, so we could just use write tag, which is kind of an identity function. And that should be part 2. So if I run this whole thing, my part 1 answer is still the same, and for part 2 I get HCFZCC something something, which is indeed the correct answer. So this is not the shortest nor the most efficient way to do it, but I thought it was pretty cool how you can solve a problem like this, just doing like a bunch of matrix rotations. I thought that was neat. And then a lot of people were complaining about the parsing because it's vertical rows rather than horizontal. But I think in APL, at least with the use of transpose, it's actually not that bad. Most of our length in the parsing function here is just getting things into our preferred format for the matrix that we were using. So that is day 5. Thanks for watching.